Hello, everyone. I just want to talk about going further in this course, and if you're interested in learning beyond this course. So, if you are actually, certainly let Professor Kwan know, and I'd be happy to teach a second semester version of this course. And there's not a lack of things to talk about, so there's plenty of stuff to do in the second semester. And I'd probably, well, I don't know if I'd go any faster, but if people wanted me to, I would go faster. I should mention before I say anything, we didn't have time to prove that the Hilbert transform on the unit circle, or rather on 0 to 1, is LP bounded. But that would probably be the next natural thing to do. And beyond that, we would look at um, operators that are called Calderon-Zygmunt operators on Rn, which are basically integral operators in some sense that behave like the Hilbert transform. Okay, and there's a nice Wikipedia page on Calderon-Zygmunt operators that are quite interesting. And this subject gets really interesting because you often want to do this and not necessarily Euclidean space. If you're taking Professor Zhu's course, a perfect example is the Bergman projection. From L2 of the unit disk to the Bergman space. That Bergman projection, basically, with respect to a metric other than Euclidean metric, it's a variation of the hyperbolic metric. With respect to this metric, the Bergman projection behaves kind of like the Hilbert transform. Okay, so it is a Calderon-Zygmunt operator. It is an integral operator that behaves like the Hilbert transform. Okay, and in terms of books, if you want to go further in studying Fourier analysis, I would probably say if you ever find yourself in a position, particularly, if you're doing some PDE theory, maybe if you're working with Professor Pachanu and he utilizes some tools in Fourier analysis that we haven't gone over. Particularly, I know he uses Littlewood-Paley theory, which is kind of like an LP version of the isometry property for Fourier series and the Fourier transform, which is really beautiful stuff. Again, more stuff I would have done if I had time to do it. Anyway, yeah, if you ever find yourself needing to study more Fourier analysis than we've covered in this course, you really can't, in my opinion, do better than Loukos Graphicos's classical Fourier analysis. It's a behemoth of a book in the sense that it's 600 pages long, and there's a 600-page book on modern Fourier analysis in addition, so 1,200 pages of Fourier analysis. But it's big because it really fills in a ton of detail. It's kind of like, it takes kind of the approach that I've taken where really details are worthwhile to fill in. Yeah, and we've done a lot of the stuff in this book. We've talked about the distribution function, convergence and measure, convolution, approximate identities. We've talked about Marcinkiewicz interpolation theorem, restored interpolation theorem. I very briefly made a little mention of Stein-Weiss interpolation theorem. I didn't touch Lorentz spaces just for time reasons. I talked a little bit about some kind of off-diagonal Marcinkiewicz interpolation theorem. I very, very briefly mentioned it. I didn't really say much about it. We talked about maximal functions, Fourier transform. Avoided talking about distributions, but anyway, talked about the Schwartz space, et cetera, et cetera. Talked about Fourier series. Anyway, so yeah, this book has everything you could possibly want in terms of really Fourier analysis that you'll probably see in other areas if you doing your PhD here. Okay, another nice set of lecture notes if you really want a quick introduction, particularly to the kind of harmonic analysis that I'm interested in, which is basically called dyadic harmonic analysis, meaning it's harmonic analysis with an emphasis on using dyadic intervals and dyadic cubes in higher dimensions, and kind of using these to prove properties about Fourier transform, Hilbert transform, et cetera, et cetera. This is a really nice set of lecture notes. It's an introduction, and it's very short, but it still gets into a lot of beautiful stuff. It's not as detailed as my videos are. You have to fill in more detail, but still, I mean, so in really chapters 1 and 2, they go over basically all the stuff I've spent a lot of time on going over, and then it immediately gets into some really beautiful things. You can see here, right? And this kind of stuff, I should mention, there's a strong connection to probability theory in the sense that for anyone who's familiar with more advanced probability theory, we use techniques from martingales quite a bit. I don't know if anyone's took Professor Hildebrand's graduate probability course. I don't know if he's talked about martingales or not. I think he did. But yeah, so very, very strong connections to probability theory. And I'll put this PDF in the contents section. You can just really Google Maria Cristina Pereira and go to her website and download this. Yeah, I forget where I downloaded this book, to be honest, but it's around. And I think our library has it, but right. So yeah, and if this all intrigues you and you want to learn more about it in a course, certainly talk to Professor Kwan, and I'd be happy to teach a second semester in this. Not a lack of stuff to talk about. And if I did teach a second semester, I would probably actually use these lecture notes. I think they really nicely kind of extend, they very nicely extend my videos and my lecture notes. Right, so all right, well, hope everyone had a nice Thanksgiving. Basically, we're over. So good luck with grading and et cetera, et cetera. And so long, take care. Have a good winter break. Stay safe, and yeah, take care. Bye-bye.